Hi, good morning and welcome to this session. In the last session we have seen the temporal difference models and its mathematical development, why it is called temporal difference model, etc. Now we will discuss how to find optimal policy for TD0. In the next session we will discuss SARSA model. SARSA means state action response state action model. First of all, we will see what is optimality of TD in terms of Monte Carlo. We just try to compare optimality operations in Monte Carlo and the new temporal difference models, and we mathematically validate the operations in our temporal difference model will leads to optimal policy. And finally, we will show you how to represent a Markov reward process in terms of state diagram and how we can interpret this Markov reward process in terms of temporal difference learning. First of all, we will see what is optimality of one-step temporal difference or TD0. The first point is the temporal difference model will learn more compared to MC method. It is very trivial because in temporal difference model an agent start from a state S and take an action to move into the next state S dash. Then how it calculate the reward? It is very straightforward. It calculate the reward as the immediate return R plus the return up to the state V of S dash, value at the state S dash. That is R plus some gamma into V of S dash. But remember, in Monte Carlo method, to get the return GT, the agent should try a traversal from the state ST till the end state. Then only it can calculate the return. That means the agent will have to wait until he get an experience about a full traversal. It will take much calculations that depends on number of states, and so this optimization take much time. But in the case of TD model, it is only a one-step transition learning, so it learn fast just looking into next state value. That is why we can say that this TD model will learn more. This agent will learn more in TD setup compared to the Markov chain approach. The second point is a TD0 may update the estimates with respect to the step index, state index T, either state wise or episode wise. That means when we look into an environment, the agent can update the state value just state wise. From second state it can learn the reward, and using the return at second state it can calculate the reward and also the value at the state S as R plus gamma into the next state value V of S dash. Okay, this is one option. It can calculate all state value within the episode. The second option is the agent have to wait till one episode completes. Then he update the value of each state V of S using the formula. V of S is updated to the initial V of S plus alpha into that R plus gamma into, that is our temporal objective or temporal target, that is R plus gamma into V of S dash minus V of S. That happened only at the end of the episode. That is another one option. If it is doing at the end of the episode, it is called episode wise or batch wise updation. That means it can this agent can update the state value immediately after its visit at a particular state, or just wait until it complete one episode, just update the weights. There are two possibilities. Okay, in state wise approach it will update within the episode. In batch wise the value function is updated at the end of the episode. So there are two options. Okay, now in the coming 2 slides we are going to discuss the optimal state values leads to optimal policy. I repeat, the optimal state values will leads to optimal policy, because in dynamic programming approach to Markov decision process, and also in Monte Carlo we have some specific methods. Whenever the state value functions or state value function and also the state values becomes steady, or it will not change considerably within the iteration, that means the system is steady in terms of state values. At that situation, automatically the policy will be optimal, because there is a competitive and cooperative learning happened in this DP environment. Now we are going to establish more probabilistically, whenever the state values become stable, the corresponding policy is optimal. We are using a different approach, that is a usual machine learning approach. Under batch updating, TD0 converges deterministically to a single answer independent of the step size parameter alpha, as long as alpha is chosen to be sufficiently small. This statement is very much clear from this definition. See, at the end of the last point I have given the state value updation formula in TD, that is V of s is updated by initial V of s or the current V of s plus alpha into R plus gamma into V of s dash minus V of s. Now what happened where this alpha is very small? Alpha is very small, this quantity become insignificant. That means V of s is updated by almost same V of s itself, and that means the system is stable at that particular state. That particular state there is no scope for improvement in Vs. It means state value at the state S is steady. If it got for every state, we can say that in terms of state value that environment is steady, that model is steady. Okay, so this is a direct consequence of focusing on the values of alpha. Remember, alpha lies between 0 and 1, that is open interval 0, close interval 1. That means it takes all the values between 0 and 1, but 0 is excluded. Okay, now batch Monte Carlo method always find the estimates that minimize mean square error on the training set. Now we bring back our machine learning terminology, the mean square error and training set, etc. Okay, here training set means that the number of different episodes that the agent tries to learn our state values. Number of different episodes the agent tries to learn state values using the complete return. That is the idea. That is the meaning of training set here. Then mean square error. We are familiar with mean square error. Just for explaining the terms, I just rewrite what is mean square error. Mean square error means mean of square of errors. So first we'll start with error. Error means V of s is our calculated value minus g is the return. So actual value minus expected value. Here actually g is our actual value. I just write this in time because there is no problem, because v of s minus g the whole square is same as g minus v of s the whole square. Even though this term is negative, on taking the square that negative will disappear. Okay, so 1 by n of s into sigma v of s by g minus g the whole square gives MSE. Error means difference, square is square, mean means total by total number, so sigma is total. This n of s means number of times that particular state s visited. So we got 1 by n of s into sigma v of s minus g the whole square, that is mean square error. Then when does the mean square error is minimum? This mean square error is minimum by classical calculus when the first derivative is equal to 0 and second derivative is greater than 0. That is the idea. We can use the concept of divergence, gradient. Del is equal to simply partial derivative. Then I take 2 times 1 by n of s is a constant, then derivative of this expression that is derivative of x square is 2x. So derivative of v of s minus g the whole square is 2 times. I take this 2 outside. Then v of s minus g into derivative with respect to this v, that is again 1. Then how we got this minus? I just interchange this term. I take a negative outside. V of s minus g the whole square is actually equal to 2 times v of s minus g. That can be written as minus 2 times g minus v of s. Now, in order to minimize this negative expression, we have to maximize the positive expression. Now look, this is for the complete episode, but we are deriving the formula for step by step or iterative formula. In that state, we can exempt the sigma. Then consider this term 2 by n of s into g minus v of s. See, it's a negative expression. To get minimum of this negative expression, it is enough to maximize this. So maximize this expression. I exclude this sigma. This 2 by n of s is incorporated in this alpha. So g minus v of s is here. So iteratively, minimization of this mean square is same as maximization of this expression. Maximizing this expression means we try to iteratively maximize v of s. We try to maximize iteratively this v of s. See, what is my aim or the agent's aim? Agent is try to maximize each state value. So whenever the agent tries to maximize this iterative formula, then automatically the mean square error is minimized. Now we just repeat this statement. Bosch Monte Carlo methods always find the estimates that minimize the mean squared error on the training set. This Monte Carlo tries to minimize this mean square error. Automatically this update maximize the state value. Now we think about TD method. Bosch TD0. Instead of Monte Carlo, we just focused on TD0. TD0 always finds the estimates. Estimates means the value of v that would be exactly correct. See that? Exactly correct for the maximum likelihood model of the Markov process. This is the key point, because we have designed this temporal difference model as a Markov process. Then the maximum likelihood of a Markov process model will give this result. It automatically maximizes this v of s iteratively. But this is not an approximation. This is an exactly correct value. That is the advantage of using Markov process, more precisely the steady state Markov process. Whenever we are using a steady state Markov process, how can we say that is a steady state Markov process? If we are using the batch updating, we update each state value only at the end of the episode. That means this movement or transversal of this agent from start state to end state repeats many times. So it automatically stabilize the probability distribution or the state transition probability. In that case, the maximal likelihood model exactly maximize this function. What is this function? This is our TD update function. So this maximal likelihood model of this Markov process condition ensures that whenever the state values are optimal or steady, then automatically it leads to maximal likelihood exactly. Now we look into another famous idea. In general, this generalization, a batch TD0 converges to the certainly equivalence estimate. Then what is a certainly equivalence estimate? Whenever the state values are optimal or steady, then automatically the underlying model is exactly correct. I repeat, when the state values of a model are steady and correct, then automatically the model will be correct. Then what is model here? Model is governed by the policy. That policy is optimal. That policy leads to the maximum likelihood. What do you mean by maximum likelihood? Maximum likelihood means the probability to happen that particular event is maximum. The probability near to 1. So whenever the state values are updated in such a manner that there is no significant change in consecutive iteration, the state values become steady. Under that condition, using this certainty equivalence condition, this TD0 is a certainty equivalence estimate. That means the corresponding policy becomes maximal. Instead of using Bellman's optimality condition, we are using our maximum likelihood estimate of Markov process. The basic idea is that we can represent this TD in terms of a Markov process. We will see it in an example later. In normal computational architecture, we are trying to compare order of complexity of Monte Carlo and TD0 here. If cardinality of S, that means number of states, is equal to n, S means number of states in a particular model, then order of complexity under Monte Carlo is order of n square or order of n cube. That means complexity is much higher. But in the case of TD, the temporal difference learning, it is in terms of order of n. That is a difference. So computational complexity is minimum. If the computational complexity of a stepwise operation become minimum, so it is more fast. The algorithm is fast means this algorithm help the agent to learn. The learning will be fast. Okay, so whenever the number of states increases, it is better to use TD model. We just shift from MC to TD. On task with large state space, TD methods may be the only feasible way. See, underline that, only feasible way of approximating the certainty equivalent solution. When if it's a number of states becomes very much large, we cannot make use of our DP algorithm. It is not possible. It is very difficult to see our all states to get the exact rewards and returns. Okay, in that situation we cannot make use of DP. The another option is Monte Carlo. But in the previous point we have stated that if the state numbers are much high, its complexity become large. When the complexity become order of n cube, automatically the time taken to learn all these parameters takes much time. Here the parameters are state values. That means agents become lazy. If we are designing a game using such an agent, the agent will wait for the next response. It will not move. So game becomes so dull. That is another problem. So in the case of DP also, if the state values becomes large, it's better to use TD because TD is the only method. So this is the door that opens to the concept of game development using reinforcement theory. In a game there are lot of levels and lot of options to an agent. As the options increases, the game become more interesting. All the students or all the people who are interested in game expect more surprises and more difficulty levels. Okay, in that situation the aim of the developer is to maintain a balance. The game should be go on, first thing, and also he or she has to maintain a minimum number of levels and a minimum number of speed. That is the point. So the only way is this temporal difference approach. So from the next discussion onwards, we are focused only on temporal difference, because the temporal difference open some other options to incorporate some parametric approach. That means we can include parameters from deep learning also. In that case, this reinforcement learning will be elevated to another level, that is called the deep reinforcement learning. It is possible. All these are attained with the help of this new concept introduced by Richard Sutton. We are using the same textbook for dealing all these points, this temporal difference model and wide varieties of some temporal difference model. Now we look into a simple example. It's a predictor problem with the Markov reward process. Okay, it's a prediction, TD0 prediction. First of all, I will explain what is the situation. In this state, in this model, there are only two states, A and B. There is also a terminal state. We are not given the terminal state in terms of symbols. What is meant by this first line? It's a first try by the agent. This agent starts from A and he got a reward 0 and moves to B. From B to terminal state, again he got a reward 0. See, this is a nice move. He starts from the state A and end at the terminal state, his return is 0. There's something wrong there. The next time he starts from B and goes to the terminal state with a reward 1. Okay, that means the agent learned a new idea. do not go to step A. You just start from B. From B, start this journey and go to the terminal state. He got a reward 1. Repeat this 3 times. Similarly, he start with B and goes to the terminal state with the reward 1. But at the end, he start from B, but unexpectedly he got a reward 0 and goes to the terminal state. Then how we can represent this as a Markov reward process? That is the first question. From a state diagram, form a state diagram representing this Markov reward process. Why it is called a Markov process? A Markov process is a mathematical model that in that situation the movement is divided into different states, and the state probability should be known. But here the state probabilities are not given explicitly. We can calculate the state probabilities using this table. Okay, first of all, look into the table. The left side there are 4 iterations, and right side there are also 4 trials for the agent. So total 8. Out of this 8, 1, 2, 3, 4, 5, 6. 6 are favorable to B, ending at a positive return 1. And also starting from B, it leads to a 0 return. That means how many favorable positive return to B? That is first question. Out of 8, there are 6 favorable cases for B, ending with a positive return or a non-zero return. We can think like that. Then what is the probability for that non-zero non-zero return? So 6 by 8. We can simplify 6 by 8 as 3 by 4 or 0.75. This 0.75 is the probability to start from B and leads to the end state or terminal state with rewards 1. Then what is the probability to start from B then leads to end terminal with 0? You just take the difference, because this state-wise total probability should be 1. So 1 minus 0.75, that is 0.25. So basic idea we have learned in Markov process. Okay, that is about B. Now we come back to A. From A to terminal state there is only one state, but in that one state it goes 0. So from A to B there is only one reward possible, that is 0, but there is no other possibility for this agent to move from A to the end state. So the total favorable actions are from A to end state with 0 reward. So 100% of movement from A to end terminal ends with reward 0. Now we can sum it into a simple plot, and we can mark this probability and return in that plot, and that is called Markov reward process. Now look into this. Okay, start from A to B, it always gives reward 0. Look into the table. Start from A, it goes to the end terminal or terminal state. A to B, it always gives the reward 0. From B to end terminal, it also gives 0. That is in the second case. So A and B are states. We can denote this A and B in circles. Okay. Then A to B, only reward is 0. So it is 100%. Then B to end terminal with the reward 1, 3 by 4, that is 75%. Then B to end terminal with the probability 25%. Probability means 0.25, or in terms of percentage 25% with reward 0. So this is called the Markov state diagram. See, this is one state. The total transition probability for one state transition is total probability should be 1. So 100% means 1. Then what about this second stage? That means B to terminal state, state B to terminal state. Now you just sum up these vertical probabilities. Here the probability is 0.75, here the probability is 0.25. So total is 1. So the Markov conditions are satisfied. So it is called a Markov state diagram, which contains both reward and probability. So Markov reward process is a model. Now we have to identify the state values. Okay. Now look, the end terminals always possess 0 state value. Now this is my just previous state B. Then we can calculate the state value of B using these probabilities, because in this case we know the transition probability matrices. So it's very easy to calculate expected return at the state B using our DP approach. That's all. We simply calculate sigma pi of A given us into sigma P of S dash comma reward from state S with action A into immediate reward R plus gamma into P of S dash. That is our formula. In the case of DP, we can use it. So what is the expected value? 0.75. 75% means 0.75 into 1 plus 0.25 into 0. So 0 into 0.25 means 0. So 0.75 is the reward. 0.75 is the reward at the state B. 0.75. It is because the end state always have value 0. That is why V of S dash equal to 0. So we directly got 0.75 here. Now we can update state value of A using this immediate state reward of from B. Here the reward of B is 0.75. So by our TD0 we can calculate this V of A is equal to V of A plus, initially V of A is 0. 0 plus alpha into R plus, here R is 0, plus gamma into state value of this B, that is 0.75. For this case I take alpha is equal to 1 and also that gamma is equal to 1. Okay, in that situation I got A is equal to 0.75. So we got state value of B is equal to 0.75 and state value of A is equal to 0.75. This is the idea. Now we explained this. One is to observe that 100% of the times the process was in state A, it transversed immediately to B with reward 0. And because we have already decided that B has value 3/4, therefore A must have value 3/4 as well, because we just use the temporal difference learning. So we are trying to say that the Markov reward process can be viewed as a TD process. The advantage is that it is just look into next state value. It will never start a traversal from the start state to the end state, or it will swipe over all other states associated with that state using DP algorithm. So it is more convenient. It is something like that. In order to predict the weather condition of next Sunday, we need not to wait until Sunday. We can predict it just at least Saturday evening. That is our TD difference approach. We can, in temporal difference approach, we just focused into Sunday's prediction based on current situation and current environment. That's all. This update. In another way, we can predict Sunday's climatic condition on Saturday. How? We just stand on Saturday, that is ST. Now we look into Sunday's condition. How we can we look into Sunday's condition? You just read the values from the weather forecasting sensors. From that we will create some approximation, and we look into this immediate reward. Immediate reward may be our from our experience. If the atmosphere is cloudy, then there is a chance for rain in the coming few days or something like that. Make use of all this information. We can predict the value of Sunday just prior. It's possible. So that is the advantage of temporal difference. Then we can update this prediction by make use of the reward and our assumption. The difference between the reward and assumption, our original reward and our approximation or our expectation. We do this. Here expectation doesn't mean the average. Here it is simply our initialization or some assumption like that. That means we just think like that. We start with an initial assumption for a state value, a particular state. then we will update this assumption with the help of temporal difference. The temporal difference is the helpful idea. Temporal means time difference, something related to time. Temporal difference means we take a difference in these predictions or difference in prediction of our returns using next immediate state value. Next immediate state value only. Okay. So let us conclude this session. In this next session we will see SALSA model. Now we have seen what is temporal difference prediction, then how we can calculate the state values and how we can identify the policies, etc. Now we think about the optimal policy identification. For that we need some control algorithms. SALSA is a control algorithm. Control algorithm means it's a generalized policy iteration approach. We start with an initial policy, then we calculate the state values, then we try to identify an action which gives much better state value, then add it into the policy, or policy is revised or improved. Then we repeat this process iteratively, and finally the model will be stable. In that situation, using our existing criteria, we can say that the state values are stable, and so the model is exact, and so the underlying policy can be considered as the best fit policy to the present environment under the present situation. Okay, thank you.